This video is looking at topic number 5 of your energy notes. So you need to go and get the energy notes out and look at topic number 5, and you're going to follow along in those notes. Most of the information that we're going to cover in this video is already written for you in those notes, so it's just a matter of filling in some extra information and just highlighting some key ideas that we look at throughout this video. And we're going to focus on just methods of heat transfer or energy transfer, and also what's called specific heat capacity. First, to start off, we're going to just talk about thermal energy. Now, thermal energy, when you read through the definition, you're going to recognize it's very similar to what we refer to as total mechanical energy. So if you remember that from topics 3 and 4, when we talked about total mechanical energy, we were combining both our kinetic energy and our potential energy together. So we did a couple of examples outlining that. The Wile E. Coyote example, where we looked at gravitational potential energy and also kinetic energy together, and we classified that as total mechanical energy when we added those two energies together. Thermal energy is the same idea. You're going to take total kinetic energy and then the potential energy, and we're going to add those two together. Now, you'll see that when you go from your thermal energy, when you start talking about your thermal energy, it's dependent on some key factors. So when we look at the mass, the temperature, the nature, or the state of the substance, those all determine the amount of thermal energy within any given substance that we will examine in physics. One of the key components here, and this is really where we're going to focus on energy transfer a little bit later on in the video when we actually do some calculations. Now, this is a really key point, because when we talk about thermal energy and how it moves, the energy always goes from high energy, so I'm just going to call that HE or He. We always go from high energy, or what we would perceive as lots of heat, so something that's hot, and that energy is transferred to a low energy. And that is always okay. We always move from a substance with high energy to a substance of low energy. That's the transfer direction of energy. And you can feel that even yourself. And like in the winter, right, when you are beside a window, the window, that area around the window, you always feel a little bit cooler. And that's because you are generating energy, right, in the form of heat. You feel cool because you are a high energy compared to the low energy of the window and also the atmosphere outside the window. So what you feel, why you feel cool, is because the energy is leaving your body or being transferred from your body to the outside or to the window. And so because of that loss of energy, you feel cool. Just like when your body actually, when you get hot, you purposely sweat because you create an energy transfer. So your high energy, the sweat helps you transfer that energy out of your body. Now, the other component, so that was thermal energy. The other component we like to focus on is the idea of temperature. And temperature, to really just put it simply, you're really just measuring the average kinetic energy of the molecules in a substance. So when you stick a thermometer inside a substance or in a liquid, you're really just measuring how quickly that kinetic energy is moving around. So you're really measuring the speed of those molecules. The more kinetic energy you have, the faster they go. And when you think of the kinetic molecular theory, which is something that you probably would have taken in chemistry, you know, the more energy you add, the faster those molecules go, and that's really what the thermometer is actually measuring. Now, we're going to look through ways this energy is actually transferred. So we're really focusing on what we would primarily look at is temperatures, the temperature transfer, or how does energy transfer around or in a substance. So the first one is conduction. So when we think of conduction, we think of, or when we look at conduction rather, we are transferring energy really from one atom to another, and it's through a series of collisions. So again, just to put the candle example here, so a couple things you can think about. So this here, if this was a conductor, so say it was a metal, and you stuck it in the fire, well, gradually, molecule by molecule, the energy transfers up the piece of metal that you've put into the fire, and eventually it reaches your hand. It'd be like you roasting marshmallows, right? You're going to use, say, a coat hanger, and you stick the coat hanger in the fire as you're roasting the marshmallows. Eventually, the coat hanger becomes warm on your hand, and that's because the energy is gradually moving up the substance. And you can kind of think of it as if I just drew a bunch of little dots here, and each of these dots is representing a molecule within that substance or that conductor. And energy, if this is my heat source down here, the energy just gradually moves from molecule to molecule, and that's a key. It's transferring from molecule to molecule. It doesn't jump over molecules, because as the energy is added, think about what molecules do, right? They're going to vibrate back and forth more. They're going to rotate around, right? They're going to oscillate, but they're not physically going to move from one position to another. So as you add more energy and you jostle around and those molecules are bumping into each other, you create friction, right? And that frictional heat keeps going up the rod. So that's the idea of conduction. The next one is looking at convection. Now, convection current, the key to convection current, and something that you should really focus on here, is it is moving in an air or a liquid substance. So convection does not happen in a solid. And the reason convection works is because molecules can actually move around within the substance. So they can deliver or transfer energy from one area to another by physically moving around. Whereas conduction, which happens in a solid, can't do that. Right? So conduction, the molecules are fixed, whereas convection, the air or liquid molecules can actually move around. So if you look at this diagram, as a simple pot, right, we're going to heat this water, right? So we have our heat source here. That's going to warm the water at the lower level in the pan. And as water or liquid increases in temperature, what will happen is the molecules will rise to the top, and they become, with the energy from the element and it's heating it up, it becomes less dense, and that's the reason that the molecules move up. So they become less dense, the molecules move up, and they're actually transferring energy as they move up to the top. And when they transfer the energy, then they become more dense. And they become more dense because when they transfer their energy, the molecules then will slow down and they'll become closer in contact or closer proximity, and then they will move back down. And you get this cycling action, right? So you get energy going up, it cools, and then it falls down because it becomes more dense. It gathers more energy down here. So this is your energy source. And then it transfers that energy up. Once it transfers that energy up, it becomes more dense. And then it falls. Those molecules then will go back down and then to gain the energy. So you really do get this cycling action. It's rotating around. It's a convectional current. You've probably heard of convectional ovens, right? Energy is being circulated around the oven, and it's being sped up by a fan inside just to help that circulation of energy throughout the oven. We're going to spend a little bit more time on convection in another example a little bit later on, but that's another method of heat transfer, and again, that's happening in an air or a liquid substance. The last one is radiation, right? And this is energy being transferred by, again, electromagnetic waves. You'll spend a lot more time in this in grade 12, but electromagnetic wave is really a photon of light. That photon, what you want to think of it as, is just it's a bundle of energy or a package of energy, and that package of energy is transferred from the sun, and it can move all the way from the sun, and then it can enter our atmosphere. And the unique thing about this photon of light, it's a bundle of energy of a whole bunch of different wavelengths, but what's very unique about it is that it can actually move, and it can move without a medium, right? So no medium is required for it to move. So that means that you don't need to transfer energy from molecule to molecule to molecule. It's like this little transport truck of energy, or this little package of energy that's just sent from the sun, travels down, and then once it enters the Earth's atmosphere, then it strikes different substances and molecules and so on, and then it can transfer that energy and then transfer it through the process of convection and conduction. But the energy itself can actually travel without the medium. Now, it's very high energy. So if you think of yourself at the beach, there's always a whole spectrum of energy that's going to hit you. There's a visible portion, and then there's also other wavelengths that you can't detect but are very high energy and can penetrate deeply into different substances. And if you think of the dangers of getting a sunburn or a suntan, that's because you have a spectrum of energy that can penetrate quite deeply into your skin and can eventually cause some damage. So just to quickly look at the electromagnetic spectrum, again, just to emphasize here that, when we talk about electromagnetic wave, or when we talk about a photon of light, it is the whole spectrum of wavelengths. Now, when we get into the sound unit, we're going to talk about wavelengths and how they work. But for now, what you really have to focus on is that, radiation is another way energy is transferred. And its special condition is it needs no medium. And then if you think back to convection, its special condition is that it's in an air or a liquid, so molecules are free to move. And in conduction, molecules are fixed, so it has to go from molecule to molecule. Now, we're going to now start talking about what's called specific heat capacity. So now we've kind of generalized how energy is transferred, and now we're going to look at the special properties of different substances, and we define those heat capacities, or that ability for substances to absorb or give away heat, in terms of what's called specific heat capacity. And if you think back to grade 9, we talked a lot about density. That was a physical property, a quantitative physical property. Specific heat capacity is very similar. It is specific to substances. So you can have, aluminum. It will have its own specific heat capacity compared to gold, compared to lead, compared to magnesium, right? They all have their own specific heat capacities, and those are all dependent on the type of substance, right? The chemical and physical composition of those particular substances. So when we look at specific heat capacity, we want to examine the substance, and the substance itself is going to be a 1 kilogram piece of material, right? We're going to take 1 kilogram, and what we really want to look at is, well, how much energy does it take to raise 1 kilogram of a substance 1 degree Celsius? And that's all that specific heat capacity is dealing with. Specific amount of energy to raise 1 kilogram 1 degree Celsius, and that's kind of our standard that we would look at. The measured amount, or the units, is joules per kilogram degrees Celsius. Now, that in itself tells you the definition, right? So joules is the energy, right, per kilogram, right? That's our standard mass that we're going to compare. And then we're looking at degrees Celsius. And again, when we look at the definition of specific heat capacity, that's what we're concerned with. We're looking at how much energy, how much mass, and how much temperature is it going to increase. And every substance, again, is going to have its own unique specific heat capacity. Now, the equation that we use for specific heat capacity is looking at, again, those particular factors, right? We're looking at mass. We're going to be looking at temperature change. And we're going to look at the quantity of energy, which is going to be the Q. And then C is your specific heat. Nope, let me just draw a different arrow. Let me just go right up here, right? That's your specific heat capacity, right? So that's what the little c stands for, the lowercase c stands for. So again, we can define that, and it's probably written in your notes, right? Again, our standard unit for mass is kilograms. Specific heat capacity is the lowercase c, and then we're looking at temperature change. And again, this is key here. We're always looking at final temperature minus initial temperature, and it's always a capital T, because a capital T is representing temperature, whereas a lowercase t would represent time. And so when we start talking about specific heat capacity and calculating specific heat capacity, then we are going to look at whatever the final temperature is of the substance versus its initial temperature. Now, we're going to look at an example question, and we're going to look at how that example question uses that specific heat capacity. So this would be our basic specific heat capacity equation. So the wording of the question is, how much energy is needed to raise the temperature of 2.8 kilograms of water from 30 degrees Celsius to 45 degrees Celsius. Now, a couple key things here. The first thing you want to look at is obviously the mass of the substance, right? We want to know how much of that substance do we actually have to add energy to. So the more mass, the more energy that we're going to have to put in. The second thing we want to look at is the temperature change. Now this is a positive temperature change. That means that the substance is going to gain energy. And so when the substance gains energy, then we always make that change positive. And again, if you look at your delta T, or your temperature change, it's equal to your final temperature minus your initial temperature. So again, this is my final, which is going to be 45, and my initial is going to be 30. So that's going to be a positive temperature change. And when we start talking about heat exchange, going from one substance to another, that's super important to know whether it's a positive or a negative energy change. Now, just popped up the solution there. So again, just to go through that, the only other thing I didn't address previously is the actual specific heat capacity of water. Now, this is what you're going to look up in your chart. So if you look at your notes, if you look at topic number 5, you will have a specific heat capacity chart. And then you'll see that one of the specific heat capacities is water. And again, that means, that number really means that it takes 4,180 joules. And if you had a kilogram of water, that would be how much energy is required to raise it 1 degree Celsius. And if you look at the chart, water is the highest specific heat capacity. And that is an important property of water because water, if you look at an environment, is very much a temperature regulator. Like the big lakes around you, that really modifies weather and climate. And that's because it holds on to so much energy, right? It takes lots of energy to heat it up. But it also holds on to that energy for a longer period of time, and it will allow it to moderate the climate and the environment around there. So again, once we get all that information in, just coming back to the question, you're going to plug that information in, and then again your answer is going to be in joules, so that would be all the energy that's needed to heat 1 kilogram of water. And again, we're assuming a perfect energy transfer. We know that that's not really the case, and you know, there's going to be mechanical efficiency that we talked about earlier, and there's only going to be a percentage of that actually going in there, and that's something that we'll investigate in another lab after exams. But for now and for the exam, you just need to know that, yeah, that's the specific heat capacity, and using this particular equation, again, you can rearrange it like any other equation. You might be asked, how do I find the mass? I need to find the specific heat capacity of a substance, or I need to find the temperature change. And so again, you can take that and you can manipulate that to find any one of those variables. The next one is, or the last topic is looking at the principle of heat exchange. The principle of heat exchange is based on the law of conservation of energy, and that really, just to put it simply, is the energy lost or transferred, and that's really a better term. We use the term lost a lot, and even the textbooks use the word lost, but it doesn't really get lost to somewhere. It's actually being transferred to another form. But the energy that's being transferred is equal to the gain of energy on the other substance. So if you had two substances in contact, and one substance was transferring its energy to the other, so we're going from high energy to low energy, then in a perfect system, all that energy is going to be transferred over. We cannot create energy. We're not going to destroy energy. We're actually going to just transfer that energy to one form to another. Now, the equation that deals with the principle of heat exchange is really just the expansion of that specific heat capacity equation. So we're going to really take the hot substance, which again I'm just going to call He, right? That's high energy. And then we're going to transfer energy to the low energy substance, or LE, right? And again, law of conservation of energy states that the hot substance is going to transfer its energy to the cold substance, and that's going to be an equal transfer, and that's why we come up with the idea that it's going to be zero. And again, that's an ideal situation. Now we're going to expand that, and when we expand that equation, we're really just taking our Q equals MC delta T, and we're just defining this as our hot substance, right? Our high energy substance. and we're defining our cold as our low energy substance, or the one that's at a lower temperature. And again, we've just expanded the Q, right? So that's the quantity of heat. So quantity of hot is going to equal to quantity of cold. And so then we know that Q equals mc delta T. And so that's why we've written that below. So we know the equivalence of that. Again, we know that's equal to 0. Or we can just rearrange that, and we're going to swing the hot side to the other side of the equation. And so because we're moving the whole thing as a unit, we're going to move it to the other side, then we need to make that negative. And again, that's an important aspect to the question, or when you use that kind of equation, that you got to make sure that's a negative on the other side. So really, the positive over here, the cold is gaining the energy, that's why it's going to be positive, and then the hot substance is going to be losing or transferring its energy away, and that's going to be a negative. So we're going to look at a practice problem, and this will be set up in your notes as well. And it's going to be looking at how much water at 100 degrees Celsius must be added to 1 kilogram of water at 10 degrees Celsius to produce a mixture with a final temperature of 37 degrees. So we got to define this in two areas, right? We got to figure out, first of all, really our hot information and our cold information. So this side here, right, we're looking at, in the end, we need to figure out, okay, the mass of the hot substance. So how much of this hot substance needs to be poured in to the cold in order to reach that temperature. So we're going to have this boiling water, we're going to pour it in, and we're going to pour in X amount in order to achieve this 37 degrees. So again, for water, they're both substances that are mixing together is water. So we got 4,180 on one side, 4,180 on the other side, because we're just mixing water and water. Same substance, same specific heat capacity. If we're mixing two different substances, then those two numbers would be different. In some of the example questions you're going to do, you're going to find that that's the case. The other aspect is looking at your temperature change. And then again, this is the important part of these questions. So when we look at the hot side, so again, it's final temperature subtract initial temperature. So the 37, 37, that's your TF. Your 100 is your initial. So we're pouring in boiling water. The final temperature is going to be 37, so then it becomes negative 63 degrees. And that negative is really important because that negative tells us that energy is being transferred from the hot water. Whereas you go on the other side, again, this is our final temperature, but our initial temperature was a lot lower. So it's gaining energy, so that's why this is going to be a positive number. And that's, again, seems like such a simple little thing, but when you're manipulating an equation, just to get those positive and negatives in the right place will determine whether you're going to get the correct answer or not. Just like when we went back to kinematics, those positive and negatives are extremely important. So, the calculation of that, again, this is your principle of heat exchange. So, again, we know that that's equal to 0. We're going to plug in our numbers here, and you're going to go through that manipulation. I'm not going to explain every single detail here, but once you go through that math calculation, you're going to end up getting that mass. And all that mass means is that you would, in a perfect system, if you poured in 0.43 kilograms of 100-degree water into our water that was 10 degrees Celsius, then equilibrium would occur, and that equilibrium would occur at 37 degrees. Alright, so that is everything about energy transfer in terms of conduction, radiation convection, the idea of thermal energy, the idea of temperature, and introducing the idea of specific heat capacity and exchange. On the next slide, you'll see that there's some homework questions. These are dealing with a specific heat capacity. And for the exam, focus your attention on using both the principle of heat exchange as well as just the specific heat capacity equation. There will definitely be some questions on that, using that equation and the manipulation of that equation. So make sure you go through those practice questions, and then again bring in any problems you have with using those two equations.